let's recall that a vector valued function is some function r of t where you input a scalar or a real number, which we're indicating by t, and the output is a vector where each component is a function of your parameter. So we have like r of t can be the vector valued function defined by f of t, g of t, and we'll carry out most theorems and computations in 3 dimensions. I want us to know that the 2-dimensional case is analogous. You just cut off. You would just stop here instead. But in the 3-dimensional case, we have h of t as well. Okay, and we learned in the last video some examples of vector valued functions. We saw what it means for the limit of a vector valued function to exist. Remember, the limit is a vector. We saw that there's a handful of properties that need to hold for a vector valued function to be continuous, namely that the function at the limit exists, that the value of the limit exists, and that they're the same, right? And so now we can take this a step farther, just as we did when you think back to Calc 1. What did we do after we learned limits? Well, we did a handful of examples to get familiar with limits, but then we used the limit to define a derivative, and that's exactly what we're going to do now. Let's look at the derivative of a vector valued function. And again, I'll abbreviate vector valued function by VVF. So the derivative of a vector valued function. Here's a definition. So the derivative of a vector valued function, r of t, is defined by, and we use a similar notation to differentiation that we're used to from Calc 1 and Calc 2. We use a prime, right? We say r prime of t is equal to, and here's the limit definition. It's the limit as t approaches a of r of t plus delta t minus r of t all over delta t. And so this is the limit definition of differentiation. This is probably the most rigorous and time-consuming if you want to use this definition to actually calculate the derivative. It's important that we can be able to use the limit to calculate the derivative, and we'll do some of those examples in our recitations. But for now, let's just see here that this is the rigorous definition of the derivative, and then let's go right to our theorem that allows us to compute derivatives much easier and much quicker. So let's let f, g, and h be differentiable functions of t. And what do I say when I mean differentiable? When I say differentiable, I mean r prime of t exists. So that's when I say differentiable in the setting of vector valued functions. When I'm saying differentiable here, I mean that, I mean that f prime, g prime, and h prime exist, right? And so when I say, if I say that a function is differentiable, intuitively what I'm saying is the derivative exists. So let's let f, g, and h be functions of t if r of t is differentiable right? And this time when I say that r of t is differentiable, I mean r prime of t exists. Then, so if we write, let's say R of t is f of t, g of t, h of t, then r prime of t, which is the derivative of r of t, can be expressed component-wise. We can express r of t, or r prime of t, as f prime of t I hat plus g prime of t j hat plus h prime of t k hat. And so we can calculate the derivative component-wise. And this makes perfect sense because if you recall in the last video, we learned that you can calculate limits component-wise. The limit of a function just means you, or the limit of a vector valued function just means you take the limit into each component, and then you can compute limits component-wise. Well, then since the derivative is simply a limit, right? At its core, the derivative is just a limit. Well, then that means we just pass the limit component-wise and then express it as a derivative, which means that we indeed get this nice property that to calculate the derivative of a vector valued function, we just need to calculate the derivative component-wise. And so let's see a quick example. If r of t is the vector valued function e to the t sine t, e to the t cosine t, and negative e to the 2t, let's find r prime of t. Okay, what is r prime of t going to be? Well, r prime of t means we just calculate the derivatives in each component. So I'll write this out here. It's going to be d dt e to the t sine t. And then in the next component, it'll be d dt e to the t cosine t. And then in the third component, it's going to be d dt of negative e to the 2t, right? And so now we just have three Calc 1 derivatives to take here. The derivative of the first component, you can see, is going to be a product rule. So we go derivative of the first times the second, so e to the t sine t, and then plus the first times the derivative of the second, so e to the t cosine t. Use the product rule again, but now for e to the t cosine t, it looks like we're going to get e to the t cosine t minus e to the t sine t. And here we use the chain rule to get that the derivative is negative 2 e to the 2t. And so here is r prime of t. And all we had to do was compute three single variable derivatives to calculate the derivative of this seemingly complicated vector value function. Now, just like there's a lot of analogy between how we learned single variable derivatives in the introductory calculus class versus what we're learning about derivatives of vector valued functions now. Namely, there's a lot of properties that the derivative of a vector valued function enjoys. So let's look at properties of the derivative. Right? And here there's a handful of properties that have not been previously discussed because now our outputs of these vector valued functions are vectors. And so we need to understand what how does vector addition work with the derivative? How does the dot product work with the derivative? How does the cross product work with the derivative? These kinds of things are the properties that we're going to explore here. And so the first one is just a property of scalars, and it's to say that if you take d dt times k, or d dt of k times r of t, that, well, the first one is a rule of scalars that you can just pull the scalar out front. So this is indeed k times d dt of r of t, and then here we'll just let k be an r. So k is a scalar. The next property I'd like to discuss is, whoops, 2 here, is a property of vector sums and vector addition. If you take the derivative of the sum or difference of two vector valued functions, so let's say we're taking r of t plus or minus u of t, right? Sorry, that doesn't look like a t in there. U of t. Then this is the same as the derivative of r of t plus or minus the derivative of u of t. And so for vector valued functions, we can still split the derivative over sum and subtraction. 3 here is the scalar product rule. Scalar product rule says that if we take the derivative, so to make sure I have room here, let's say we're taking the derivative of now a scalar valued function times a vector valued function, right? Here, f of t is not a vector valued function. It's just a standard scalar valued function where you put in a number and you get out a number. And we want to see what happens when you take the product of a scalar function with a vector valued function. What's the result? Well, there's a sort of product rule that we have to abide by. And namely, I'll use prime notation from here on out. This is f prime of t times r of t plus f of t r prime of t. So it seems just like the product rule where you take the derivative of the first times the second plus the first times the derivative of the second, or like f prime g plus f g prime, right? We have this, and when it's just f of t, a scalar function times a vector valued function, we have this product rule. We also have the dot product rule. The dot product rule says that if we have the derivative of the dot product of two vector valued functions, let's say r of t dot u of t, well, this also satisfies the product rule, but now it's the dot product. So we have r prime of t dot u of t plus r of t dot u prime of t, where these are dot products, right? We have something extremely similar for the cross product. We have a cross product rule. So if we're taking the derivative of the cross product of two vectors, so let's take r of t cross u of t, well, this is r prime of t cross u of t plus r of t cross u prime of t. And so these are all very similar to the product rule. It's the same flavor, right? Where you take the derivative of one times the other plus the other one times the derivative of the first one, right? So it's a very similar flavor, but we have this for the scalar product, dot product, and cross product. Lastly, there are two more I'd like to talk about. We have the chain rule. The chain rule says that if we take the derivative of a vector valued function of a function, so we have this kind of like scalar function embedded in a vector valued function. Well, then this is simply the standard chain rule. It's r prime of f of t. It's the derivative of the outside times the derivative of the inside. This is what the chain rule says, right? The derivative of the outside is r prime. You leave the inside alone, times the derivative of the inside, which is f prime of t. Okay. One more rule that I'd like to discuss here, which is an interesting rule to think about. And I'll let you guys kind of ponder this and see if you can understand what is this trying to tell us. It says if the dot product of a vector valued function with itself is a constant, then r of t dot r prime of t equals 0. So this is a nice property that can come in handy, especially in like a physics application. But I think it's a worthwhile thought exercise for you guys to try to understand, like use your knowledge of the dot product here and say like, what does this mean? Like, and see if you can prove this to understand what's going on here. Great. So we have this long list of properties here of the derivative. One is, so to recap quickly, it's to say that you can pull a scalar out front. The second one says that the derivative splits over plus and minus. Here we have a scalar product rule. We have a dot product rule. We have a cross product rule. They all have the same flavor, but for their respective products, right? One is just scalar product, one is dot product, one is cross product. We have the chain rule. And we have this condition, if the dot product is constant, then the dot product with the derivative is 0. So now that we've seen the derivative and some properties, let's apply these. Let's see what kind of formulas and what kind of useful information we can get now that we know vector valued functions and their derivatives. The first one, so let's start to look at some applications of derivative. First one I'd like to talk about is tangent vectors. Okay, so if we have some curve given by a vector valued function, r of t, right? Let's take a given point on this curve and say, okay, what's a tangent vector? We want a formula for a tangent vector. Right? Well, we know from like Calc 1, if you have like y equals f of x, and then you look at a point, what does dy dx give you? Dy dx gives you the slope of the tangent line. So derivatives and tangent lines are very much so intertwined. So finding a formula for a tangent vector to a curve, right? Something like this with initial point on the curve. So it's not a very good picture here. So we have initial point on the curve, and then we have some tangent vector. Let's call it capital T here. How can we get a formula for this? Well, we need a vector that is orthogonal to r of t. And by the previous property, if r of t dot r of t is a constant, then the dot product of r of t and r prime of t is 0. And if that's 0, that means this is orthogonal to my previous vector, which makes it a tangent vector. So we can get a tangent vector by simply taking the derivative. Our derivative can be a tangent vector. And now what we'll define is, I'll have the right definition here. This is the principal unit normal, unit tangent vector, not unit normal vector. We'll get there later. Unit tangent vector. And it's given by capital T of t equals r prime of t over its magnitude. So you calculate the derivative, calculate its magnitude, and you have a formula down here for the principal unit tangent vector, which gives you a vector of magnitude 1 tangent to your curve. And so for a circle, the tangent vector kind of around the circle would look something like this, right? And you can see here, like at theta equals pi, it would be vertically down. theta equals 2 pi or 0, it's vertically up. It's horizontal to the left at pi over 2, horizontal to the right at 3 pi over 2, right? And so here's our formula for the principal unit tangent vector. And so this is the first application of the derivative. And before we go to more applications of the derivative, I would like to first introduce integrals of vector valued functions. And once we have integrals of vector valued functions, we can use derivatives and integrals together to get a plethora of applications. So let's first look at the integral or integrals of vector valued functions. Let's let f, g, and h be integrable over the interval a, b, right? And integrable just means the integral exists. Then we can define the integral of a vector valued function. Then the integral of vector valued function r of t is defined as follows. Okay, I'm going to use the next page because we need to define indefinite and we need to define definite integrals. So let's start with indefinite. Indefinite integral here. So we have the integral of r of t dt. Okay, and this is equal to the integral. Integrals enjoy, or vector valued functions, the integral of a vector valued function enjoys the same property as limits and derivatives. Because how is an integral defined? Well, you take a sum, you take some finite sum as an approximation, and then you take the limit of that sum. And so when we take the limit of that sum, we know that that passes to each component. And because of that, we can say that if r of t is f of t I hat plus g of t j hat plus h of t k hat, just like we've been defining r of t, well then, since the limit splits component-wise, we can also split the integral component-wise, right? So this is f of t dt I hat plus, so let me, for the sake of being more thorough, let's write out in a bit more steps here. What is the integral of r of t? It's the integral of f of t I hat plus g of t j hat plus h of t k hat dt. Now, by my previous reasoning about how the limit, since the limit of a vector valued function passes to the limits in each component, so does the integral. And this becomes the integral of f of t dt I hat plus integral g of t dt j hat plus integral h of t dt k hat. And so this is nice when we're calculating integrals as well. We just pass integration to the function in each component, right? And now for indefinite integrals, let's say the antiderivative of lowercase f, g, and h is uppercase f, g, and h respectively. When we take indefinite integrals, we know we pick up a constant, right? We pick up a plus c. And so what is this integral equal to? Well, it's going to be like f of t, the antiderivative plus some constant c1 I hat, plus the antiderivative of g plus some constant c2 j hat, and then plus the antiderivative of h plus some constant k hat, right? And so we can express this now as f of t I hat plus capital G of t j hat plus capital H of t k hat. And then notice we also have this vector here, C1, C2, C3. And we can write this even farther is if we take, I'll erase it here. Let's call this C1, C2, C3, let's call it C here. Now our constant of integration is a vector and not a number. So the constant of integration, let's make a note, for vector valued functions, the constant of integration is a vector, not a number, right? Not a number. For the indefinite integral, you have the integral of r of t dt equals, and this is like, again, f of t, g of t, h of t plus c, where this vector c is defined as c1, c2, c3, which are the constants of integration from each component's integral, which c1, c2, and c3 are numbers, right? But the constant of integration for a vector valued function is each of these numbers in a component that makes up one vector. So that's worthwhile. And lastly, we can talk about the definite integral. Vector valued function. Okay. And now the definite integral means we're taking the integral over some interval, right? Integral from a to b of r of t dt. And by the same argument, this passes to the integral a to b f of t dt I hat plus integral a to b g of t dt j hat plus integral from a to b of h of t dt k hat, right? And so then when taking the integral or taking the definite integral of a vector valued function, you just pass to the definite integral of your component functions, right? And definite integrals have no constant of integration, right? That vanishes when you look at a definite integral. And so, you know, by the fundamental theorem of calculus, you could write this one step farther and say, okay, well then this is, let's write it in vector component form. This is like f of t evaluated at b and a. This is g of t evaluated at b and a. And this is h of t evaluated at b and a, where again, capital F, G, and H are the respective antiderivatives of F, G, and H, right? And so using the fundamental theorem of calculus, this would just be like f of b minus f of a, GB minus GA, and then H of B minus H of A. Okay, and so there's some formulas for computing the definite integrals of vector valued functions. And I think this is a pretty natural place to break. And in the next video, we'll kind of circle back to applications. We'll see how can we calculate arc length? How can we calculate curvature? Let's see some physics examples using calculus of vector valued functions. So that'll be for the next video. I will talk to you guys then.